Okay, take a deep breath. We're going to start with new concept, which is the derivative. This is, I think, the main breakthrough that we're going to have in this course. So you may need to watch this multiple times, or you may need help after this. This is normal. This is fine. You shouldn't feel discouraged if that's the case. This is difficult to understand the first time you see it. If you have seen it before, then you don't need to worry about it. You're going to understand everything that we're doing right now. Okay? But just try and be careful and try and pay attention because this is important and this is the main object of study of this class. Okay? Which is derivatives. So remember that we started this chapter by talking about the tangent, finding the tangent line to a curve and finding as well the velocity of an object. So we had a specific goal of solving what we called the tangent problem and the velocity problem. And we're going to figure this one out by using limits. We sort of came up with a strategy of what we were going to do, and that strategy allowed us to use limits. So this is the first expression I want you to pay attention to. Hold on, give me a second. Okay, sorry, the neighbor's dogs were making too much noise. Alright, so this is the first expression you have to pay attention to. We hinted to this in the very first motivation video that we talked about in the chapter. We want the tangent line to a graph, and we start by looking for the slope, because we already have a point. Right? They're supposed to give us a point. So all we need is the slope. And we figured out by looking at our graph. You have some curve like this. And we want some point here. And we want the tangent line to that graph. So a line that only barely touches the graph over there. And we do that by choosing, so this is point P. We choose another point Q somewhere. And we look at the secant line. And the slope of that secant line is this MPQ. Okay? And we make Q get closer and closer to P by using limits. Okay? To make that be the tangent line. Because you can see that as we choose a Q that's closer to P, then the line through P and Q gets closer to the red line. You're going to have better representations here. Okay? This one's very good. As Q gets closer and closer to P, then the blue line gets closer and closer to the line T, which is the red line. Okay? So here's the first definition. The tangent line to the curve y equals f of x at the point P, a f of a, is the line through P with slope m given by this limit, which is the limit of f of x minus f of a divided by x minus a as x approaches a, provided that this limit exists, which is crucial. If it doesn't exist, you'll have to verify anyway. So it is crucial that it exists for a tangent line to exist, but if it doesn't, then you're going to find that out anyway while you try to calculate the limit. See an example. Start it. So we have a parabola y equals x squared. We know how the graph looks like. We know it's something like this. Do it in blue. And they're asking for a equals 1, so we're at 1. F of 1 is, so y equals x squared, right? So 1 squared is 1, so this is the point we're at, and we're looking for the tangent line here. Okay, tangent line here. We already know that point 0.11, right, is part of my line. So all I need to find now is the slope. So we find m equals the limit as x approaches 1, right? This 1 right here of f of x minus f of 1 divided by x minus 1. And now I start doing my math. Okay, understand what I did first, understand how I came up with those numbers, and I wrote them down, understand the idea of the formula for the limit, and once you do that, then we can work on the numbers, because the numbers are secondary. We've already worked on limits before. You know how to calculate limits at this point. The most important thing is to understand why we calculate this limit and why this one, right? How we get to this formula. But from there, let's go. So f of x is x squared. F of 1 is 1 squared, which is 1. I can also just look at the second coordinate here to get f of 1 if I want. And the bottom is just x minus 1. Add a page. Do I have space here? Yeah, I have space. Don't need to add a page. So this is limit. Sorry, I forgot to write the limit, right? So it's the limit. X approaches 1. You have to write it always. This here is by the difference of squares. This is x plus 1, x minus 1, and that's divided by x minus 1. So that's the limit. X goes to 1. I can cancel this with this. The only situation in which I would not be allowed to cancel is if x equals 1, in which case that would be equals 0. But when we have x approaching 1, you want x very, very close to 1, but not equal 1. Right? So that's x plus 1 instead. And then m equal, just plug in, right? Direct substitution property, or x plus 1 is a polynomial which is continuous. That's 1 plus 1, which is 2. So m equals 2 is the slope of my line. I also know that my line goes through the point 1, 1, right? So my line will be y equals mx plus b. I know m equals 2, so y equals 2x plus b. So let me break this apart. So now I go point 1, comma 1 is in the line, so, or on the line, whatever. One equals 2 times 1 plus b. 1 equals 2 plus b. B equals minus 1 by subtracting 2, right, to the left. So y equals 2x minus 1 is the tangent line to y equals x squared at p1, 1. Okay? The real breakthrough was finding the slope. Again, it took thousands of years for people to figure this one out. It took a very long time for people to understand how this had to be done. And I think you now have the tools to understand. So if you don't, just go back and think. Again, watch this again if you need. Pay attention to the very first video of the chapter and why we have been discussing that we needed to find the limit, or the limit of the slope of the secant line, to find the limit, to find the slope of the tangent line. Okay? So the slope of the tangent line is, sometimes we say the slope of the curve, because it's the same slope. It's the line that touches at the right slope, so it doesn't cross or cut the line or the curve. And the idea is, from what we're saying, if we zoom in far enough, the curve looks almost like a straight line. And this is what's going on, right? If we zoom in, look at the size of this. It's even a little blurry. Look at that. Look at the size of this viewing window. It's very small, like 0.2, and this looks very much like a line. This idea is going to be important later, because sometimes when you have difficult equations to approximate, you can use a line to approximate it using the derivative of the equation, which in general is simpler. Okay? And this, again, is the idea. The more you zoom in, the more the parabola looks like a line. In other words, the curve becomes almost indistinguishable from its tangent line. Okay? Here's another expression for finding the tangent that's usually easier to see. And that's because you just, rather than looking at x minus a, you fix a, and you look at a and a plus h. And then you go f of a plus h minus f of a, which is the same, I guess, like the the vertical, right? This vertical thing here. And then you look at, and let me use the yellow one, this is change in y at the top, right? And then the change in x is h, right? A plus h minus a, which is h. Okay, this length is h. So this is what we have. It's another expression. I prefer this one most of the time. But it depends, it varies. And sometimes I'll even use one that's different. I'll say f of x plus h minus f of x divided by h. This way I get an expression, so in x and h, and I replace x if I need to. We're going to see an example of that later. Okay, you're going to see that. This is, again, my favorite. It's what's called, if you remember from pre-calculus, we did a few examples that included this quotient. It's called the difference quotient for a reason, right? Because it's important. It comes down to this. Let me pause real quick because I want to show you something.